Okay, so now that we actually know how to derive differential equations for circuits and solve differential equations, we're actually ready to analyze some circuits. So in particular, in this class, we're going to look at the configurations that are relevant to this class, which are basically RL circuits, RC circuits, and then there's also RLC circuits, and then there's also LC circuits. So let's start with this RC circuit shown here. So to derive a differential equation, we can just simply realize that the voltage drop across the resistor plus the voltage drop across the capacitor have to be equal to Vn. So we're going to have that Vn equals Vr plus Vc. And like we said in our previous lecture, we always want to solve for capacitor voltages because remember that the current going through a capacitor IC equals C ddt of Vc. And so that means that Vc has to be a continuous quantity, otherwise the derivative wouldn't be defined for certain inputs in time. And so what this allows us to do is that now we can actually write Vr in terms of IC. So basically we have that this is just equal to ICs of t times R plus VCs of t. That should be equal to Vn. And then we can use our IV relationship to convert this into Vc. So we're going to get that this is just RC ddt of Vc's of t plus Vc's of t. And then if we wanted to find our homogeneous solution, we would get that 0 equals RC ddt Vc's of t plus Vc's of t. So that's going to give us our characteristic polynomial, which is just 0 equals RC lambda plus 1, which gives us that lambda equals negative 1 over RC. So the time constant or the lambda 1 for this particular circuit is equal to negative 1 over RC. Before we move from this example, let's look at a second example where we have a current source, a resistor, and a capacitor. So this is another form of the RC circuit. Now we have a current source here. So in this particular case, we're going to have that I of t, or here I'm going to call this IN. INs of t has to be equal to IRs of t plus ICs of t. And again, remember that this is the voltage across the capacitor, which is the same as the voltage across the resistor. So we can rewrite this as Vc's of t 1 over R plus C ddt of Vc's of t. And that's equal to IN. In particular, if we wanted to find the homogeneous response, we would set this to 0, and then we could find our characteristic equation. So we would have 0 equals 1 over R plus C lambda, and that would give us again that lambda is equal to negative 1 over RC. So those are two examples of first order RC circuits. So now we've looked at this one, and now let's look at an RL circuit, and we're going to actually solve the full RL circuit. Okay, so here's the RC circuit, actually summarizing what I showed you in the previous slide. So we applied KVL to get that it's Vn times minus Vr minus Vc is equal to 0. And then we use our differential equation to get our IV relationships for the capacitor in order to get rid of the current going through the resistor. And then finally we get our differential equation. Okay, now let's go ahead and look at a second example. So now we're looking at circuits that have inductors on them. So in this particular case, very similar as before, we have that to determine our ODE, we're basically having that VNs of t is going to be equal to VRs of t plus VLs of t. And then remember that our IV relationship is that VL of t equals L ddt of IL. So ideally we would want to solve for IL. So what we're going to have is we know that VR is actually equal to, well, the current flowing through the inductor and the resistor are the same. So this is just equal to ILs of t times R plus L ddt of ILs of t. That's it. We just derived the differential equation for this particular circuit. So let's go to the next slide. So here's the differential equation that we derived in the previous slide. In this particular case, I divided everything by R. So remember that this was R times, and then there was no R here and no R here. If I divide all three terms by R, I end up with this R here, and then this R disappears, and then you end up with an R there. And so now I actually plugged in the numbers that I have from my circuit. So I had the Vn was 3 to the negative 3t, so I have 3 to the negative 3t, and then I had that R was actually equal to 2 ohms, so there's the 2, so that's why we have 3 halves. And then we got that L was equal to 1 Henry, so we have 1 Henry divided by 2. And then, yeah, so that's our final ODE. So we're also given a value for the initial condition of ILs of t. So we have that ILs of 0 equals 1 amp. So as you can see, this very much looks like a sample problem like the one we solved in the previous class. So the first step was always to take the find the V particular. And remember, to do that, we just simply assumed that our particular solution was of the form of the right-hand side, and then we plugged it into the differential equation. So that's what we're going to do next. So we assume that our particular solution is of this form. And remember, the total solution ILs of t is actually equal to IL particulars of t plus IL homogeneous of t. So this is without the homogeneous part of the solution. And now we're going to plug this into our differential equation. So we're going to have 3 over 2 e to the negative 3t equals c particular e to the negative 3t plus 1 over 2 ddt e to the negative 3t. And that's going to give us, oh, and there should be a CP here. Well, that's going to give us CP e to the negative 3t plus, or minus 3, so minus 3 over 2 CP e to the negative 3t. So I took the derivative of my particular solution, and something magical now happens because you can see that this, and this can be factored out. So we get that 3 halves equals 1 minus 3 halves, which basically turns into 1 half CP, negative 1 half CP. And that gives us that CP is actually equal to negative 3. Okay, so now we know that ILP of t is equal to negative 3 e to the negative 3t. So the next step is to actually find our homogeneous solution and use the initial conditions. Okay, so here we found what CP was, and now we're going to go ahead and find the homogeneous solution. So we found a particular solution. So to find the homogeneous solution, we first have to solve the characteristic equation. So for this particular circuit, I'm actually going to do it symbolically first. So remember that this was just IL of t plus L over R ddt of ILs of t. And so my homogeneous equation would be that this is equal to 0, which gives me that 1 plus L over R lambda equals 0, and then that gives me that lambda will always be R over L negative. Okay, well, in this particular case, R over L, in this particular case, if I don't do it symbolically, I'm just going to have 0 equals 1 plus 1 over 2 lambda, and that, of course, gives me that lambda equals negative 2. Okay, so now that we know that lambda equals negative 2, we now know that our solution I else of t is going to be equal to negative 3 e to the negative 3t plus c1 e to the negative 2t. And now we can use our initial condition, which was that I else of 0 equals 1 in order to find our c1. So we have that I else of 0, which is just equal to negative 3 plus c1 is equal to 1. And now that gives us that c1 equals 4. So as you can see, once you've derived the differential equation, it's just like solving the differential equations as we described in the previous lecture. So finally, we're going to get that I else of 0, I else of t equals negative 3 e to the negative 3t plus 4 e to the negative 2t. And that's it. That's our RL circuit. As you can tell, both RL and RC circuits can only have kind of one kind of homogeneous response. And for the RL circuit, it's going to be e to the negative R over LT. And for the RC circuit, it's going to be e to the negative T over RC. So they're not very interesting circuits. In order to get something different from a decaying exponential as your homogeneous response, you need to go to second order circuits. So now you know how to solve first order RL, first order RCs. You should at this point be able to deal with something that looks like this. So let's say I gave you kind of R1, and then there's an L here, and then there's an R2, and then this is V in, and then this would be IL. So you should be able to analyze something that looks like this for an exam, or something slightly different from what we've deviating in class. But again, to analyze this, you just simply derive the differential equation. And once you have your differential equation, you solve it using the same steps that we've come up with. All right, so, okay, so now we're actually moving on to second order circuits. And we're first going to look at our LC circuit, which actually will give us an undamped response, or as we will see, our characteristic equation will have purely imaginary roots, and it's going to have exactly 2 of them. So here's the, so we're going to first have to derive the ODE for this particular circuit. So to do that, we have that Vn of t is actually equal to VL of t, so the voltage drop across the inductor plus the voltage drop across the capacitor. And here we have a choice. We can solve for VC or for VL, it doesn't, or for IL, it doesn't really matter. Since we wrote it in terms of voltages, let's just solve for VC. And so to do that, we need to get rid of this VL, so we have to realize that VL of t is actually equal to L ddt of IL of t. But remember that IL of t is actually also equal to the current going through the capacitor, which is also equal to C ddt Vc of t. And so here we can just plug in C dV dt, so we're going to get that actually VL of t equals L d dt of IL of t, which is equal to L d dt of C d dt of Vc of t. So this is just plugging in for IL, IC, and then plug in C dV dt. And so that's going to allow us to basically rewrite this equation as V-ins of t equals L times C. You can factor out the C because it's a constant. And then this becomes the second order derivative of VCs of t plus VCs of t. So that's our differential equation for this particular circuit. And as you will see later, the roots are actually purely imaginary. So here's that derivation that I did in the previous slide. And I could have also solved for ILs of t. It doesn't really matter. Typically, if your source is a current, then you would want to solve for ILs of t. But here we had a voltage source. Okay, so let's now find the homogeneous solution of this particular circuit. So we're going to have that 0 equals LC lambda squared plus 1. So that's going to give us that lambda 1 is equal to negative 1 over the square root of LC I, or J, sorry, because yeah, we're not mathematicians. Lambda 2 equals J 1 over the square root of LC. And I'm sorry if I write J's, I's instead of J's. I'm actually used to using the I notation, and I know that we're supposed to use the J notation, so my brain just fights me on it continuously. And so what we said is that if we have imaginary roots, we would use sines and cosines. And so actually we're going to get that the homogeneous solution, so VC homogeneous of t, is going to be some constant B1 cosine t over the square root of LC plus B2 cosine t over the square root of LC. And that's basically it. So what that means is that this kind of circuit will give you a homogeneous response that's basically some kind of sine plus cosine of a given frequency, and the frequency is, of course, 1 over the square root of LC over 2 pi. Okay, so that's or you could put it in radians, so it's just 1 over the LC, but whatever. Anyway, so that's the homogeneous solution of this particular circuit. All right, so what's so special about this? So let's look at a simple scenario where, as an input voltage to this circuit, I'm gonna give it a decaying exponential. So basically, I'm gonna give it a really strong response, and that response will go to 0 as time goes to infinity very rapidly. And additionally, I'm gonna assume that this circuit at time equals 0, so ILs of 0 is equal to 0, and VCs of 0 equals 0. So ILs of 0 being 0 tells me that C ddt of VCs of 0 is 0. So that's just another way of saying that the time derivative of the voltage is 0. And so I'm going to assume these two things, and then I'm going to use an input of e to the negative t. So on the next slide, I write this more cleanly. So basically, I have I'm going to assume that VCs of 0 is 1. Oh, wait, I lied. So first, I'm going to assume that this input is actually 0. So first, I'm just going to assume the input is 0, and then I have an initial condition driving this. And then I want to know what the V particular is for this circuit for time equals greater than 0, and the V homogeneous. Well, since the input is 0, V particular will be 0 because it's a homogeneous problem. And now we just need to solve for the homogeneous response. And so we're going to get that, we said that VCs of 0 equals 1, and the derivative of VCs of 0 equals 2. So remember that our homogeneous solution, VCs of t, is actually B1 cosine t over the square root of LC. And then here we have L is 1/2 and C is 1/2. So we have 1 over the square root of 1 over 2, 1 over 2. And so the square root of that is clearly 1/2, so we're going to get 2. Okay, so we're going to have 2t plus b2 sine 2t, and then the derivative of this, so d dt of vch of t, is actually equal to negative b1 sine 2t plus, and then there should be a 2 in front, 2 b2 cosine 2t. Okay, so when we evaluate it at 0, we're going to get that vch of 0 is actually equal to b1 times 1, because cosine of 0 is just 1, and then b2 times 0, so that's just 0. And then we're going to have d dt bch of 0 is equal to, well, sine of 0 is 0, so this term is 0, and then this term is just 1, so we have 2b2, sorry. And then we said that the output was, the derivative was 2 from here, and we said that b is 1. Okay, so that gives us that b1 is 1 and b2 is 1. And so our final solution will just be this replaced with a 1 and this replaced with a 1. That's it. We just solved this homogeneous circuit, and so here I kind of drew it more cleanly. So here to name my coefficients, I used a's. It doesn't really matter what you name your coefficients as long as you get the correct values, which is that a2 is 1 and a1 is 1. Okay, so that wasn't that interesting. So now, but okay, something interesting here is that if this circuit is initially at 1, it means that it will continue to oscillate at infinity, even without any sources. So this kind of system resembles a pendulum in the sense that it keeps going back and forth, back and forth, back and forth, back and forth. Okay, so now we're actually going to look at what happens when we have an input. So basically, like I said earlier, we're going to look at the specific case where we have a decaying exponential input, and then we have 0 initial conditions for both the IL of t, which is equal to c ddt of Vc, and the voltage across the capacitor. So this is a completely discharged example. And for this particular case, we have that L equals 2 and C equals 2. So that's going to give us that 1 over the square root of LC is just 1 over square root of 2 times 2, which is just 1/2. Okay, so it's asking us to solve for VCs of P. So to determine VCs of P, I'm just going to go to the next, actually I can do it right here. So in particular, like we just need to write out the differential equation. So we said that V ins of t, which is equal to e to the negative t, is equal to LC ddt squared VCs of t plus VCs of t. And L times C in this particular case is just 4. And so we can just plug in, we can create our guess for VCPs of t as just a constant C0 e to the negative t, which is the form of Vn. And then we plug it into our differential equation. So we're going to get that e to the negative t equals, the second order derivative of this is just -1 times -1. So we're going to have 4 -1 plus C0 e to the negative t plus C0 e to the negative t. And so that's just going to give us that this is just equal to 5 e to the negative t times C0. So that means that C0 has to be equal to 1 over 5. Okay, so now that we know what VCP is, we're going to use the same techniques that we used for the analyzing differential equations in the previous lectures. Now we need to find the homogeneous solution. So I'm going to do that in the next slide. Okay, so in the previous slide we got that BCP was equal to 1 over 5 e to the negative t. and it was positive. Yes, it was positive. And then we also know that the differential equation was that the homogeneous differential equation would be 0 equals L times C, which is 4, ddt squared squared Vc sub t plus Vc sub t, which basically gives us that 4 lambda squared plus 1 equals 0. And that's what's going to lead to our roots, or our lambdas, being equal to j plus minus 1/2. Of course, we also could have just used that the lambdas are always 1 over the square root of LC, which is 1/2. Okay, so now we know that our homogeneous solution is of the form, B homogeneous is of the form B1 cosine t over 2 plus B2 sine t over 2, and the derivative of the homogeneous solution is just going to be negative B1 over 2 sine t over 2 plus B2 over 2 cosine t over 2. And finally, we can apply our initial condition. So basically we have that Vc of 0, which is equal to Vc particulars of 0 plus Vc homogeneous of 0. So in this particular case, Vc particular is this. So we have 1 over 5 e to the negative 0, which is just 0, plus Vc homogeneous of 0. So here the cosine is 1, so we're going to get B1. And then the sine is 0, so we don't have to write it. And that should all be equal to 0. So this gives us that B1 equals negative 1 over 5. And then the derivative of Vc sub 0 has to be equal to the derivative of Vcp sub 0 plus the derivative Vch of 0. So the derivative of this is just negative 1 e to the negative t. So we're just going to get, so basically here, d dt of Vc of 1 over 5 e to the negative t is just equal to negative 1 over 5 e to the negative t. So we can basically plug that into here. So we're going to get 1 over 5 negative plus this term is 0 at time equals 0. And then this second term here is just B2 over 2. And that should all be equal to 0. So we're going to get that B2 is actually equal to 1/5 times 2. So 2/5, 2 over 5. Okay, so now we have our final solution, which is basically that Vc sub t is actually equal to 1 over 5 e to the negative t plus minus 1/5 minus 1 over 5 e to the negative cosine t over 2 plus 2 over 5 sine t over 2. Is that correct? 2 over 5? Yep. So that's it. That's the full solution to this particular circuit. In the next slide, I show this much more cleanly. So first, we solve for B particular. So like I said, our initial guess will be that Vc particular is of the form a constant times e to the negative t. And then we take the second order derivative, and that's just going to give us 1. And then this will give us 1. So we have 5 e to the negative t, and so that's where we got the 1/5 in the previous slide. Check. We have that our roots are actually negative plus or minus 1/2 or 1 over the square root of LC. So that makes it so that our homogeneous solution is of this form, and the derivative of the homogeneous solution is of this form. And then finally, we just need to apply our initial conditions. So remember that this is just Vc sub t 0. and this is just d dt of Vc sub 0. So we need to match our initial conditions, and that allows us to find the coefficient in front of the cosine term, and then find the coefficient in front of the sine term. And then finally we have here the full response. Okay, so that's basically the it. So that solves our problem, and so now we can actually go and look at RLC circuits. Okay, but before we do that, I just wanted to kind of show you something interesting here, which is that as we have our input response that induces this sinusoid, and then eventually kind of we turn off our source, but the sine goes on and on and on and on. So that voltage across the capacitor keeps oscillating even though we shut down our voltage source. This is actually analogous to an oscillator. So if we consider the differential equation for the height of this ball at any given time, the height would actually oscillate up and down, up and down, up and down, up and down. And this kind of solution is called undamped because it never actually decays. So when we look at RLC circuits, we're gonna look at damped responses, and we're gonna actually look at this much more closely. Okay, so now we can actually start talking about RLC circuits. Okay, so now we're gonna actually look at RLC circuits, or second order circuits. And in particular, RLC circuits can only give us 3 types of responses. And those, of course, depends on how the roots behave. So if we have 2 distinct real roots, if you recollect, our solution would look something like this, where you have 1 exponential, 2 decaying exponentials. And so our homogeneous solution will just look like a decaying exponential. Now, in the case of repeated roots, you can have a different kind of response. So that's what we would call critically damped. And our solution can actually look something looks like this. And then finally, if we have complex roots, we're going to have a sine or a cosine that's being damped by an exponential, e to the negative sigma t, where sigma is actually the real part of the root. So just in general, as we look at these RLC circuits, what we're going to get is basically differential equations that simply look like this. And then these differential equations have a second order derivative. So we're going to get a second order characteristic equation. And the lambdas, in general, depending on whether this term and this term are the same, in which case you would have critically damped or the same roots, or if this term is bigger, then you're overdamped, and then if this term is bigger, you're underdamped. So we're going to actually look at RLC circuits, derive the equations, and then figure out how the circuit's components, as they change, move us through all of these different types of solutions. Okay, so let's look at our RLC circuit, and this should be familiar for you as we actually derived the equation for this particular circuit in the previous little sub-lecture. So we want to find a differential equation in terms of Vc. So for this particular case, we know that Vn has to be equal to Vr plus VL plus Vc. That's just KVL. Just KVL. That's it. Now we know that the current flowing through the circuit, I, is actually equal to C ddt of Vc. And so that means that we can just rewrite this term as R times C ddt Vc, or the resistance times the current is equal to the voltage drop across the resistor. And then here we can rewrite this term here as L ddt of C ddt of Vc plus Vc's of T. So remember that the voltage across an inductor is L dIL dt, but in this case IL is just C dV C dt. And that's it. We just derived our differential equation. So now what we're going to have here is that Vi's of T equals RC dd. So here, let me write this in a more clean fashion. So I'm actually going to divide everything out by LC so that I have LC down here. And then I'm going to have the second order term. The LC's will cancel, so I'm going to have d dt squared squared Vc's of T. And then I'm dividing this by LC, so I'm going to get plus R over L, so the C's cancel, d dt of Vc of T, and then I'm going to have Vc's of T over LC. Okay, so that's the differential equation for this particular circuit. And the reason I divided by LC is so I could have a 1 here, so that now my characteristic equation looks like this: R over L lambda plus 1 over LC, basically equals 0. All right, so let's look at the next slide. So here's kind of the equation I derived on the previous slide. And then that led to this particular characteristic equation. And now we can actually find what the lambdas are by plugging this into the quadratic formula. So we're going to have B, which is R over L. So we have negative R over L over 2 plus minus the square root of R over L squared minus 4 times AC, so that's 4 over LC. And that's actually what I wrote here. I mean, this is just okay. I can actually, in this particular expression, I actually put the 2 here, and then I put the 2 inside the radical so that it would become a 2 here, and then it would cancel out this 4, so that it would be written in this form here. All right, so let's now kind of look at this circuit in a little bit more detail. And let's look at what happens to, how do these roots evolve as we change the circuit parameters. Okay, so in particular, we know that lambda was going to be equal to R over 2L plus minus the square root of R over 2L minus 1 over LC. And there's a squared here. Now, in general, if this term here is bigger than this term here, then you're going to have that this will be a non-zero real number because the thing under the square root will be positive. And so what that's going to mean, if this term is bigger, is that you're going to have 2 distinct real roots. So you're going to be, in this case, when R over 2L squared is greater than LC, your solution will actually look something like this, or like a decaying exponential. We call that overdamped. Why is it overdamped? Because it's decaying very rapidly. So damped really means decaying more rapidly. So when we say overdamped, we mean it's decaying very rapidly. Now, whenever this term here is not bigger, but it's exactly equal to this term here, we're like at a transition point. At that point, we're going to have repeated roots of R over 2L. That's what we're going to call critically damped. So we reduce the damping, basically. So now we're critically damped. And lambda will be R over 2L. And then the final case would be whenever this LC term is bigger, Then we're going to have complex roots because this thing will be an imaginary number. And the oscillation omega will actually be equal to 1 over LC minus R over 2L. And the real part of our root will be negative R over 2L. Sorry, this should be negative B. Okay, R over 2L. And so as a result, our solution will look of the form of e to the negative R over L. So remember, this is just R over 2L. So sigma is just R over 2L. C1 cosine omega, well, omega is just this thing here, plus C2 omega. And so in this case, we have a decaying exponential, e to the sigma t, times a sine and a cosine. And so this thing kind of will decay very slowly and oscillate as it decays, and we call this underdamped. So, and then finally, if we just had an LC circuit, we would have undamped. So there would be no decay. So this would just be, so this is an LC circuit. So the reason I'm drawing this is because look at how things work, undamped. So when things are undamped, there's no decay. Then there's a little decay, so we call that underdamped. Then there's a little more decay, we call that underdamped, critically damped, sorry. And then finally, there's a very rapid decay, we call that overdamped. So those are the three kinds of solutions you can get out of these circuits. And it's important that you learn how to characterize this. Now, one thing to note here is that if we look at our RLC circuit, so we have an R, and then we have an L, and then we have a C. The series RLC circuit, when we look at it, if this resistance becomes large, then all of the voltage is going to drop across that resistor. Now, if you notice here, in order to become more damped, you need to make R bigger because you need to make this R equation bigger. And so really, what you're looking at here, now if L times C is much bigger than R, then this behaves like an LC circuit. And so you're going to be closer to underdamped. And so you have to also understand that this mathematics also goes with what you would think logically. If this resistance is very small, you can approximate it by a short, and you have an LC circuit. Now, if this resistance is very large relative to this, you can approximate this as a short, and what matters is actually the resistor, and so you're going to have something that decays very rapidly. So keep that in mind as you analyze these circuits. And so that's why you see this R in the numerator, and then you see that as LC becomes bigger or smaller, you move. When LC becomes bigger, you become more underdamped. When LC becomes smaller, you become more overdamped. When R increases, you become more overdamped. When R becomes smaller, you become less damped or underdamped. Okay, so that's kind of for this particular circuit. Now we're going to look at the parallel configuration, which is kind of our last circuit that we are looking at today. And so here we have a current IR coming in here, and then we have a current IL coming in here, and then we have a current IC coming in here. And then finally, we have that In sub t is equal to I R sub t plus IL sub t plus I C sub t. And let's just solve for the capacitor voltage since that's what's common to all of them. So we're going to have here that this is just VC sub t over R. And then IL is actually equal to, well, remember that VL is equal to 1 over L, the integral from negative infinity to t, IL, okay, sorry, this is not VL, this should be IL, and then this should be VL, so tau d tau. Okay, and so remember that VL is actually equal to VC because they're all exposed to the same voltage. So we're just going to say that this is just 1 over L, the integral from negative infinity to T. And then we are going to plug in here VCs of tau d tau. And then for the last one, we're going to have that this is just C d dt of VCs of T. And then we can take the derivative of both sides of the equation and divide by C. So we have 1 over C d dt of I ins of T. So I'm going to write this one first. So I'm going to get the division by C cancels out the C's, and I'm going to get a second order derivative, VCs of T. Then I'm going to write this term here. So I'm going to get 1 times RC d dt VCs of T. And then finally, I'm going to get 1 over LC for the last one. And remember that the derivative cancels out the integral. So that's it. That's the differential equation for the parallel circuit. So let's look more into the circuit here. So here I derived the differential equation. And now again, we're going to look at what the characteristic equation looks like. Oh, ha 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 ha. Okay, so here I actually didn't use VC. I used IL as my unknown. So you could have also used IL. So I'm going to briefly go over that. So here I have basically, this is just, remember, the current across the resistor. And this is just the current across the inductor, sorry, the capacitor. And now what we have to do is basically figure out that since we know that VC is actually equal to VL, we know that that's also equal to L d dt of ILs of T. And so what we can do is then just basically take this and plug it in for VC here, and then plug it in for VC here, and that's what I did to go down here. So I end up with L over R dIL dt, L ILs of T, LC d squared ILs of T, and then I divided everything by LC to get it into this form. So now we can actually look at these characteristic equations. So we're going to have that 0 equals lambda squared, 1 over RC lambda, 1 over LC, and then we can find the roots by simply using our quadratic formula. So we have lambda is equal to negative b, so 1 over RC plus minus the square root, and there should be a 2, and remember that we're dividing by 2, so we have 1 over 2 RC squared, and since we factored in the divided by 2, we don't have that 4 anymore, and this becomes 1 over LC. So one thing should become apparent, that again, the LC part is the one that determines whether you're underdamped and overdamped. And now R, instead of being in the denominator, it sits in the, instead of sitting in the numerator, now sits in the denominator. So let's look at a slide that's similar to the previous slide, but now summarizing these roots and what kind of response you're going to get. Okay, so remember, lambda equals 1 over 2 RC plus minus the square root of 1 over 2 RC squared minus 1 over LC. Okay, so remember, if this term is bigger, we're going to be overdamped because you're going to have two distinct real roots. So distinct real roots. And so whenever 1 over 2 RC is greater than 1 over LC, then you're going to have distinct real roots. And then if we make this term smaller, eventually it will be equal to this term, and then we become critically damped. So whenever they're equal, greater, so whenever 2 over RC is greater, and then whenever 2 over RC is smaller. then they become equal, and then if we keep making 1 over 2 RC smaller, or we make our resistance smaller and smaller and smaller, we eventually reached underdamped. Now, if we look at this circuit here, again, we have a resistor, a capacitor, and then an inductor. If we make this resistance infinity, it's an LC circuit. Well, look, if we make R infinity, this term becomes 0. And then we have an undamped case. If we make R very small so that it behaves like a short, so if we make this 0, then this thing becomes overdamped. So in this particular case, we have the opposite. The smaller the R, the more important R is for the circuit. And the bigger the R, the less important R is for the circuit. And so if R is important to a circuit, you're always going to have overdamped. So R important. And if R is unimportant to the circuit, then you're always going to be underdamped. And if if there is no R, then you're always going to have undamped, which would be the LC case. Okay, so those are things to keep a lookout. And so in particular, we could also look at where the lambdas sit. So in the overdamped case, we are always going to have 2 negative real roots. Okay, so we're going to have 2 negative real roots. In the underdamped case, in general, if we actually look at the expression for our equation, for example, 1 over 2 RC, and this also applies to the series case, plus minus square root of 1 over 2 RC minus 1 over LC. Now, if we assume that this is a complex, so basically that LC is bigger, we're going to have negative 1 over 2 RC plus minus J, the square root of 1 over 2 LC minus 1 over 2 RC squared. It's magnitude. This should be a square here. Now, to find the magnitude of this vector, we have to square the real part and the imaginary part, and so we're going to get negative 1 over 2 RC squared plus 1 over LC minus 1 over 2 RC. And so the magnitude of this vector will always be 1 over LC. And so what we're going to get is actually for the underdamped case, we're going to have 2 roots with equal and opposite imaginary parts. The length of this vector will be 1 over LC, 1 over the square root of LC, sorry. So remember, we have to take the square root of that. And in particular, the displacement, the vertical displacement, will be whatever is in this parentheses here. So for the parallel case, it's going to be, what is it? Yeah, 1 over 2 RC squared square root. The magnitude of that is minus 1 over LC. So remember the magnitude of that. And for the series case, it's going to be 1 over R over 2L squared minus 1 over LC. And so in particular, just remember that it doesn't matter, the circuit will always sit on 1 over LC. And then finally, for the critically damped case, the critically damped case is when these two terms cancel each other out. you will have that, well, you're going to have that basically 1 over 2 RC squared is equal to 1 over LC. So that means that basically, and your roots will actually be equal to this. So if you draw a circle, this should also be 1 over the square root of LC for both circuits. And so the solutions should always sit on a circle, and where this is actually critically, and then this would be over, and then the green ones are under. And if you have an LC circuit, the roots will actually sit here and here at the height 1 over the square root of LC, and so this would be undamped. Okay, so if you look at the roots on the complex plane, now you get an idea of how they distribute themselves. So in particular, what you will have is that the critically damped case sits here. The overdamped cases sit either at some distance away from the critically damped location. And then if you have underdamped, they're going to sit somewhere along this axis. And then the undamped cases will sit at this node. And as you change resistance, or the importance of the resistance, you're going to basically go from overdamped to undamped, and then it's going to start moving towards towards critically damped, then it's going to move towards underdamped, and then eventually we'll get to undamped whenever R is not important. So you should understand this, what people used to call the circle of death, as it might show up in an exam. You should understand what all these symbols mean. Okay, so that's RL, RC, RLC, LC circuits in a nutshell. We're going to go over solving one example, and there's actually some more in these slides, but I'm not going to actually go over them because at this point you kind of get the gist of it. Okay, so let's say we have this series RLC, and so here's the equation for the RLC circuits, and now we're told that R equals 2 ohms, L equals 1 Henry, and C equals 1 farad, 1/2 farad. So we can just plug in the 1/2 for the capacitor, and then here we have 2 over 1 and 1 divided by 1 over 1 times 1/2 and times BC. So that's going to give us the differential equation of the form of this 2 becomes a 4, so we have 4e to the negative 3t equals ddt, ddt squared VCs of t plus 2 ddt of VCs of t plus 2 VCs of t. Okay, so that's kind of our differential equation. So remember we are going to assume VCP is going to be of the form of constant C0 e to the negative 3t, because that's the form of our forcing function. And yeah, and then this of course came from the question. And now we plug it into our differential equation. So we're going to have here that this is just negative 3 times negative 3 C0 e to the negative 3t plus 2 negative 3 C0 e to the negative 3t plus 2 e to the negative 3t. So that's going to give us 6 minus 6. That gives us, 9 minus 6 gives us 3 plus 2 gives us 5. 5e to the negative 3t. And then for the and then we need a C0 here. So it's going to give us that C0 equals 4 over 5. Okay, so now we know that this is just 4 over 5 e to the negative 3t. So now we just got to find the homogeneous solution. Okay, so to find the homogeneous solution, so yeah, so here's the VCP. That's what I did in the previous slide. Okay, so now that we found what the V particular was, which in this case we said VC particular was actually going to be equal to 4 over 5 e to the negative 3t. Now we need to find the homogeneous solution, and so to do that we first need to find the roots of the polynomial. So in this particular case we have 0 equals lambda squared plus 2 lambda plus 2. And when we apply this to the quadratic formula, we will get that, well, negative 2 over 2 plus minus the square root of 2 squared plus, or minus, sorry, 4 times 2, and for AC, yes. 4 times A times C. 2. Okay, so we're going to get that basically this is equal to negative 1 plus minus the square root of 2 squared minus 8, which gives us negative 4 over 2. So that's just plus or minus 1j, so plus minus j 1. Okay, so now that we have what the what the solution to the characteristic equation is, we get complex roots, so we have to choose this type of homogeneous solution. So our homogeneous solution will be of the form CH, so t equals C1 e to the negative t cosine t plus C2 e to the negative t sine t. So we need to take the derivative of these things. So I'm just going to take it really quickly, ddt VCH of t. So in particular, we're going to have here, if we take the derivative of e to the negative t here, we're going to get a sine term, a cosine term. So we're going to have negative C1, and then we're going to have a cosine term. And then if we take the derivative of this one with respect to sine, we're going to get the derivative of sine is cosine, so we're going to have plus C2 e to the negative t. And then we also need to take now here the derivative with respect to cosine, so we're going to get the derivative of cosine is negative sine, so sines of t e to the negative t. So we're going to have negative C1, so add to that. And then we also have here the derivative of this gives us e negative C2 multiplied by C. Okay, so we have our derivative for this particular equation. So now we just have to apply our initial conditions. We also need to take the derivative of the particular solution. So in this particular case, we multiply by negative 3, so we get negative 12 over 5 e to the negative 3t. And now we're ready to apply the initial conditions that were given to us. So we have VCs of 0 is actually equal to 4 over 5 from the particular solution. And then this one's the only one that's non-zero because sines of 0 is 0. So we have plus C1. That has to be equal to 0. So that gives us that C1 equals 4 over 5. Cool. Sorry, negative 4 over 5. And then for the second equation, we have that d dt VCs of 0. Well, that's going to be equal to negative 12 over 5. And then all the cosine terms stay. The sine terms go away. So minus C1 plus C2. And then we know C1 is negative 4/5. So this becomes plus 4 over 5. That has to be equal to 0, which tells us that C2 is actually equal to 8 over 5. So 12 minus 8 minus 4 is 8. Yeah. Okay, so now that we know C2, we can get our full solution, and this is summarized in the next slide. So again, we first have to find the roots. And so we found that the roots were these, and that led to this kind of solution. And then, so now we can move on to, okay, so we have our roots. That leads to our underdamped type solution. And in this particular case, the real part, the imaginary part of our root is just 1. So this is just a 1, and this is just a 1. And the real part is just -1, so this becomes -1. So that's how we get here. Then we took the derivative to get this equation here. And finally, when we applied the boundary conditions, we got that C2 was -4/5, and that C1 was 8 over 5. Yeah, so that's basically it. So now in the next slide, we actually draw the solution, completed solution, by plugging in the values for the coefficients. Okay, so putting it all together, here it is. So now we have 4 e to the negative t, and then here we have e to the negative t times c1 times c2, and then -4 over 5, sorry, 4 over 5, and then 5/8 for c1. So here's the final solution. Okay, so is this circuit critically damped, overdamped, or underdamped? The answer is underdamped because we have complex roots or a homogeneous solution of this form. And so you have basically that your homogeneous solution will look something like this, where you decay. It doesn't necessarily have to start at 0, but that's our homogeneous solution. Okay, I'm actually going to go over one more example. If you're tired, you can check out. I mean, at this point, you kind of get the whole gist of how to solve these circuits, but let's go over one more. Okay, so first we're going to find the ODE for this circuit. So in particular, just remember that we have 3 currents coming out of here. So we have IR, IL, and IC. And in particular, we're going to try to write all of these in terms of the voltage across the capacitor. This one's pretty easy because you just have VC over R. This one, just remember that this is just 1 over L, the integral of from -infinity to t, V, V sub tau, d tau. So here, let me just rewrite that. V sub tau, d tau. And remember that they're all exposed to the same voltage, Vc, so we can just call this Vc. And then this is just equal to C ddt of Vc sub t. So we can write all 3 voltages in terms of the, all 3 currents in terms of the voltage across the capacitor. So that's what I'm going to do right now. So I have basically I in sub t equals Vc so over R of t plus 1 over L, the integral from -infinity to t, Vc sub t, tau, sorry, d tau, plus C d dt of Vc sub t. And remember, whenever we have an integral, we have to take the derivative to get rid of that integral. And I'm going to just go ahead and divide by C. So I'm going to get 1 over C d dt ions of t equals, I'm going to write this term first so that I get d dt squared Vc sub t. Then this term second, so 1 plus 1 over Rc d dt of Vc sub t. So remember that I divided by C and took the derivative of both sides. And so plus 1 over LC, and the derivative is going to cancel out the integral. Okay, so now we found our differential equation. I'm going to plug in the parameters. So we have 1, 1, and 4. So we have d dt of I ins of t, d dt squared Vc sub t plus 1 over 1 d dt of Vc sub t plus 1 over 4 VCs of t. So I just plugged in basically 4 for L, and then for R and C I plugged in 1. Now I can figure out whether it's underdamped and overdamped. To do that, I need to basically solve the characteristic equation. So I have 0 equals lambda squared plus 1 over 4. So that's going to give me negative 1 over 2 plus minus the square root of 1 squared minus 4 times 1 over 4, which is equal to negative 1/2 plus minus 0. So I have repeated roots, and whenever I have repeated roots, my solution will always look at like my homogeneous solution will look at like e to the negative t over 2 plus c to t e to the negative t over 2. And so as a result, we're actually critically damped. Okay, at this point, I'm done with the differential equation. Let's actually go ahead and try to solve it. So I'm going to delete all of this stuff except for, well, actually up to here, because we need the differential equation. But okay, so first we need to solve for B particular. So to do that, we're going to assume that the form, so I'm going to plug in e to the negative t here, so that this just becomes negative e to the negative t, negative e to the negative t. And so I'm going to plug in VC particular of t is just going to be equal to a constant e to the negative t. And now I need to figure out what that constant is. So when I plugged it in here, I'm going to get negative 1 times negative 1 VC. So I'm going to get basically negative e to the negative t equals negative 1 C0 e to the negative t plus C0 e to the negative t plus 1 over 4 C0 e to the negative t. Did I do this? Oh yeah, I have to take the derivative here, so this becomes a negative 1. Okay, well, this is negative 1 minus 1 plus 1/4 is just 1/4. C0 e to the negative t. So this gives me that C0 is actually equal to negative 4. Okay, so we found the particular solution, and we also have the homogeneous response. So now let's find the total response. Okay, so let's find the total response. So to find the total response, we basically have to now apply the initial condition. So remember that BCs of t will actually be of the form negative 4 e to the negative t plus the homogeneous response, which is just equal to C1 e to the negative t over 2 plus C2 e to the negative t over 2 and then a t. And then the derivative of this thing is just equal to negative 4 or positive 4 e to the negative t plus, or should I say minus, C1 e to the negative t over 2, and there should be a divided by 2. And then we should have here minus C2 e over 2 e to t e to the negative t over 2, and then plus C2 t e to the negative t over 2. Okay, so now I'm going to apply the initial condition at 0 to find C1. What's going on here? To find C1. And so I'm going to get here basically, negative 4 times e to the 0, which is basically 1, minus C2 over C1 over 2. And then this term, sorry, not C1 over, it's just, sorry, okay, plus C1, and then this term will go away, so that's just 0. So that's going to give us, and that should all be equal to 0. It's going to give us that C1 equals 4. And now we need to basically apply the initial condition for the time derivative. So we're going to have 4 plus C1 over 2. Negative C1 over 2 is just equal to minus 2, because remember C1 is just 4. This term is 0 when time equals 0, so we're going to have plus C2 have to be equal to 0. So that's going to give us that C2 is actually equal to negative 2. Okay, so now we found all of the values, so now we're going to get that VCs of t is actually equal to negative 4 e to the negative t plus 4 e to the negative t over 2 minus 2 t e to the negative t over 2. That's it. That's the total solution to our circuit. Okay, just like all of them, I typically type up the slides. So again, here's the derivation of that differential equation. And because we have repeated roots, we are critically damped, just to reiterate. So here's actually the solution to our circuit. And here I derive basically all of the same equations that I just derived on the previous slide. And you can see that we get the same answer.